We're on page 8. Stationary points. Remember that we found a stationary point when the tangent was equal to 0. In other words, it's when the slope of your tangent line is horizontal. Well, your tangent line is horizontal, and the slope would be equal to 0. So that happens in certain situations, and there's 3 situations where it can happen. The first 2 we've kind of looked at already, a relative maximum or a relative minimum. The third one, a stationary point of inflection, well, that happens in an x cubed graph. Remember, an x cubed graph looks like this? At 0, 0, it actually flattens out so much that if you drew the tangent there, it would be completely flat. Sometimes when we graph x cubed in grade 12, we kind of do it really quick and we kind of make it look a little bit sloped there, but it actually flattens out perfectly. And that's a third type of stationary point, which we're going to call a stationary point of inflection. So when we talk about relative extrema, that's like a local maximum or a local minimum. They're just a maximum or a minimum in their area around. But if we're talking about an absolute or a global extrema, those are extremas that are the biggest in the entire graph. And there is our point of inflection on an x cubed graph. It flattens out, but the graph stays increasing. So to find maximums and minimums, we have a couple of tests. And the first test we're going to look at is the first derivative test. Any ideas what the second test is called? Oh, you're amazing. You are so, that's like, this is why you are in calculus. Because you can figure things out like that, right? Yes, but okay, the first derivative test. Used to find maximums and minimums. So if a function has a critical number at c, okay? So first of all, we need f prime of c to equal 0, because that's what makes it a critical number. Then you're going to have a relative or local maximum if the derivative changes from positive to negative, and you're going to have a relative minimum if it changes from negative to positive. The way that we're going to see this is really easy, because you know the sign diagram that we made already. Whenever you find your derivative to equal 0, you would mark that point as c. And then you'd plug in values into your derivative. For a relative maximum, your derivatives would be positive, which means your function is increasing, and then they're negative, which means it's decreasing. It's really easy to see from those arrows that that would have to be a maximum. So if it changes from positive to negative, that means your original function was increasing then decreasing. It has to be a maximum. And 2, same thing if you found your point c, and when you plug things into your derivative, you originally got a negative number in your derivative, and then a positive number. It's really easy to see from that diagram that that would be a minimum. So if the derivative changes from negative to positive, and it's equal to 0, then you know you have a local minimum. If the derivative changes from positive to negative, and the derivative is equal to 0 at point c, then you know you have a maximum. So we have a local maximum when your function changes from increasing to decreasing. And you have a local minimum when it changes from decreasing to increasing. And this curve sketching part, we're really, really interested in finding those maximum and minimum points. So here's another question that you know what it looks like. Y equals negative x squared plus 5x minus 7. It's a parabola that opens down. So you can already tell, without any calculus, that this is going to have a maximum point. Okay? But we're going to find that maximum point and show it's a maximum with our first derivative test, which I think in a lot of ways is easier than our old techniques of finding the maximum, like completing the square. So if we want to find the first derivative test, we're going to need to have our derivative. So bring the 2 out in front, subtract 1 from the exponent. There's our derivative. Set our derivative equal to 0. So if we want to find a critical point, we set our derivative equal to 0. And we get x is equal to 5 over 2. With the first derivative test, we then make a number line with all of our critical values on there. And remember, critical values are not only where the derivative is equal to 0, but also if you have any non-permissible values. Now this is a parabola, its domain is everything. There are no non-permissible values. So the only value we're going to put on here is 2.5, or 5 over 2. And now we plug things into our derivative. Any value less than 5 over 2. 0 seems to be an easy one to do mental math with. If I plug in 0, can you see that you'll get a positive number? Meaning this function is increasing. If you plug in something bigger than 5 over 2, like 10, you're going to get a negative number, which means the function is decreasing. So if I wanted to be really like wordy and write lots of words and sort of like write an English essay on this, since the derivative changes from positive to negative at x equals 5 over 2, and f prime of 5 over 2 is equal to 0, because we figured out that when you plug in 5 over 2 in for x, y prime would equal 0. We know that 5 over 2 comma, now how am I going to find the actual y coordinate on the actual graph? I would have to plug that back in to the original equation. So I would have to say, right, when x equals 5 over 2 or 2.5, got some mental math to do here. Okay. Yes? Figured it out? Is it? I might need some help. Someone with a calculator tell me if. Whew, is that right? No? Nobody's checked it yet? That's what I'm hoping for. Oh, I'll scroll back up so you can check it. Is good? Yes! We know know that, oh, we have to finish our English essay here. Since the derivative changes from positive to negative at x equals 5 over 2, and f prime of 5 over 2 is equal to 0, we know that this point is a maximum. "17 words. Would you like it at the end of these questions if I say, write a 17-word essay to explain your answer? Yeah, that would be okay. Perfect. Now, you knew that that was a parabola that opened down, but now this diagram reiterates that. It says that same thing, and it shows us that 5 over 2 is a maximum value. Okay, here's one for you to try. How did you do? Found your derivative. Did you find that at 2 it was equal to 0? And so if I plug 2 back into my original equation, the point is 2 comma negative 3. And every time you make your statement, you're going to need two things. You're going to need to state that it was equal to 0, since f prime of 2 is equal to 0, and 2, since it changes from decreasing to increasing, or the derivative changes from negative to positive at x equals 2, we know that that is a local minimum. So the diagram shows it, and our statement shows it as well. Now, if you have a graphing calculator, you can find maximums and minimums on your graphing calculator as well by putting the graph in. Is everybody, if I have, I'll quickly put in this equation that we just saw here, which is, which one did we have? 2x squared minus 8x plus 5. Is that the one we just did? Yeah. So if I do 2x squared minus 8x plus 5, and I graph that, there's the parabola. If I want to find that minimum with my calculator, I can go second, calculate number 3, the minimum. It asks you for a value to the left of the minimum. My cursor is already on the left side, so I push enter. Then it asks you for a value on the right. You can do that by either arrowing over until you get to the right, or by typing in a number. I can see that 3 is definitely to the right of it. Then it draws 2 arrows, and if your minimum is between those 2 arrows, you can push enter again, and it finds it at, ooh, interesting, 1.9999996, 3. Now, we know from the calculus we did that it's exactly at 2, 3. But this shows us that our calculator has some error in it. In fact, the program that it uses, the calculator has a program that it uses to find the value. And once it gets close enough, it says, that's good. I'm close enough. I feel good. And so this one decided to stop when it got this close. But in reality, the answer is at -2, -3. So there's still room for improvement on this calculator. Stationary points of inflection. We have a stationary point of inflection. So what happens here is like the x cubed graph, where if you drew a tangent, it is equal to 0. So we still have the same thing that our maximum and minimums have, is that you find your derivative, and if the derivative is equal to 0 at that point, but if we drew our number line, so let's say this happens at point C, comma, f of c. If you drew your number line and put point C, the derivatives on this side, can you see that they would have a positive slope? And that our original function is increasing? And any derivative I find on this side, oh, it also has a positive slope. And that means it's still increasing. So it didn't change from increasing to decreasing or decreasing to increasing. The derivative stayed the same sign. So as a result, we have a stationary point of inflection. If we have a stationary point of inflection, the second derivative will also be equal to 0. So later we're going to find out that inflection points are actually points on the graph where your graph changes the curvature. Notice in the yellow part, we would say in the yellow part, it's concave down. It's kind of like a sad face. Because you're not feeling good, you're feeling a little down, concave down. But in the green part, this is called concave up. Right? You're feeling happier. You're like, oh, long weekend coming up, everything is good. Concave up. And when it changes from concave down to concave up, that's an inflection point. Sometimes we don't have, this is a special kind of inflection point because it's an inflection point and it's also stationary. It also has the derivative equals 0. But we have some graphs, which we'll see later, right? Part of this is sad. Part of this is happy. Where does it switch? Right there. About right there. That would be an inflection point, but it's not a stationary point of inflection. Because if I drew the tangent right here, it's not equal to 0. So we'll learn about inflection points a little bit later. This is just a little preamble to that. So we're going to look at the following graphs and sketch them and talk about all their stationary points. And the exciting thing about these ones is that they are ones that you couldn't do well otherwise. X cubed plus 3x squared plus 1. Well, if we want to find any maximum, minimums, or stationary points of inflection, we're going to use our first derivative test. We're going to find our derivative, 3x squared plus 6x. We're going to set our derivative equal to 0 to find our critical points. I can factor out a 3x, leaving me with x plus 2. It's equal to 0 when x is 0 and x is equal to negative 2. Make my number line. And by plugging values into our derivative, we're going to find out whether it's increasing or decreasing or what's happening. So if I plug in a value less than negative 2, and again, I find this really helpful to plug in things into your factored version. If I plug in negative 3, can you see that this is negative? And this factor, negative 3 plus 2, is negative. And a negative times a negative is positive, telling us this section of our graph is increasing. Then, if I plug in a number between negative 2 and 0, like negative 1, this section's still negative, but this section, when I plug in negative 1, will be positive. A negative number times a positive number is negative, so now it's decreasing. And finally, if I plug in something larger than 0, both of those factors will be positive, so it's increasing again. So what's negative 2 going to be? Maximum, minimum, or stationary point of inflection? Maximum. What's 0 going to be? Minimum. Okay? So if I wanted to write my essays, okay, I can say -2 comma, now I'd have to plug that back into my original equation. -8 plus 12 is +4 plus 1. -2 comma 5. Oh, let's write a whole essay with actual. Is a maximum since f prime at -2 is equal to 0 and f prime of x is it's greater than 0 before x equals -2 and f prime of x is less than 0 after x equals 2. So we have the two things for the first derivative test. We show that the derivative is equal to 0 at that point, and we show that the derivative changes from negative to positive or positive to negative. In the same way, 0 comma, this is an easier one to figure out. Plug in 0, we get 0 comma 1. Oh, okay, I'm going to add a word in here, local maximum. And I'm going to add it in here too. Local minimum. Since f prime at 0 is equal to 0 and f prime of x is bigger than 0 before x equals 0 and f prime of x is greater than 0 after x equals 0. And if we sketch what we know we have the point -2 comma 5. We know we have the point 0 comma 1. And from our first derivative test from the sign diagram, we know our graph was increasing, hits that maximum, decreasing, hits the minimum, and increases after. We actually have a pretty good sketch of our graph. Which is kind of nice. Okay, I want you to try this one. All right, let's check how you did. So, first of all, we could find our derivative, set it equal to 0, factor and solve. Okay. And then you could set up your number line and plug things into your derivative. Now when you plug in something less than 0, first of all, notice that x squared is always going to be positive, no matter what you plug in. But when you plug in something less than 0, like -1, this is negative, making this first section negative. When you plug in something between 0 and 3, like a +2, that second section is still negative. It's not until you plug something after 3, like 4, that section becomes positive. So what does this mean? What are we going to call 0? 0 is going to be a stationary point of inflection. Can you see that 3 is going to be a minimum? So when we want to figure out those points, we can find out at 0, 0 by plugging 0 back into the original equation. we can find out it's 3 comma negative 27 by plugging 3 back into the original equation. So whenever we're trying to find points on our graph, we're always plugging in those x values back into our original equation. As a result, we know that our graph is going to look like this. We can draw 0, 0. We can draw 3 comma negative 27. And we can show it decreasing. And at 0, 0, it's got to level out in order to have a stationary point of inflection. Keeps decreasing until 3 negative 27, and then increases after that. Now, the one thing, if I zoom to see the entire page, okay? How would we have graphed this same equation using what we learned in grade 12? Well, you would have noticed it was an x to the 4 graph, so I have sort of like a parabola drawn at the beginning. Just because it's a positive x to the 4 graph, it's going to act the same way as a parabola, meaning it's going to go up forever in both directions. Okay? In grade 12, you would have factored this, and this actually is quite easy to factor. You can take out the x cubed, leaving you with x minus 4. And so you get x-intercepts, or zeros, at x equals 0 and x equals 4. Do you remember multiplicity a little bit? We would say that the 0 of 0 has a multiplicity of 3 because it happens 3 times. It's x cubed. And because it has a multiplicity of 3, in grade 12 pre-calculus, I know I use the word that it bends when it goes through the x-axis. We had some, like if it had a multiplicity of 2, it bounced off the x-axis. If it has a multiplicity of 3 or 5 or 7, any odd number, it bent when it went through. Well, now we can see why it's bending, because it has to change concavity, right? Here we've got concave up. Here we have concave down. So it's changing concavity. That's what an inflection point does. But you would have been able to draw that bend. You would have been able to have it go through 4 comma 0 again. So that's why I labeled that point 4 comma 0. But you wouldn't have known in grade 12 pre-calculus how far down it went or where the minimum was. You would have just estimated, oh, it goes down and has to come back up, but I don't know where that minimum is. So our calculus gets us the minimum, and our calculus also explains that bend in that graph at 0, 0.